Good morning, everyone. This is Michael Stowe, energy engineer with Advanced Energy. I'd like to welcome you to the Basics and Applications of Induction webinar brought to you by IHEA, the Industrial Heating Equipment Association. I'm the chairman for the Induction division for IHEA, and we focus on industrial applications for induction and promoting induction heating and melting throughout industry. IHEA is a trade association that represents major segments of industrial heat and process equipment industry. The Induction division provides service to our members to enhance their ability to serve their end users and their customers in the industrial process heating industry. Please check out the website www.ihea.org, and you can learn more about IHEA, and we would welcome any questions you have about that as well. As a reminder, we will be taking questions at the end of the session. You can type those in the text chat box. Also, we have 3 sponsors for today's webinar. We'd like to thank them to help make this training possible to you. Advanced Energy, Heat Treat Today, which is a publication, and Taylor Winfield Technologies, Induction OEM. We have 2 speakers today. Both work very closely with Induction. First up will be Ryan Nice, an application engineer for the Induction Heating Group at Taylor Winfield. They're responsible for capital equipment sales and various applications. Brian has over 15 years experience of induction heating and has a Lean Six Sigma Black Belt certification, which helps him to understand processes and improve equipment performance. He's spent 10 years as a mechanical engineer for induction heating equipment companies, as well as 3 years of design while attending college in the transformer switch industry. Graduated cum laude from Kent State with a bachelor's degree in mechanical engineering, and he's currently serving on the IHEA board and is an active member of ASM. Ryan will be presenting an introduction to the basics of induction. Our second speaker is Dr. Girish Dahaki, and he will be presenting some applications of induction. He is Ambrell's Senior Vice President of Global Applications with over 20 years of experience in induction, leading a worldwide team for induction applications and working with Ambrell's laboratories. He holds several patents, has authored many papers, and frequently presents at professional conferences on nanoparticle heating, heat staking, and general induction heating. He has a PhD in mechanical and aerospace engineering from the University of Rochester. And now to kick off the webinar, we'll start with Ryan Nice. Ryan, take it away, please. Thank you.
Thank you, Michael. Thanks for everyone joining, and I want to say thanks for IHEA for putting this on, and I'd like to thank Garish from Ambrell as well, who will be hosting the second portion. This is basics of induction. So my discussion topics will be what is induction heating, what components make an induction heating system, what applications can use induction heating, and then I'll give a few application examples, and then we'll follow up in the end with a Q&A. So induction heating. So induction heating is the process of heating electrically conductive materials using controlled time-varying electromagnetic field that is transferred to the workpiece. This field causes the workpiece to heat up due to high-density current induced from the work coil to the workpiece. A time-varying electromagnetic field is a field that changes intensity or strength with respect to time, which at any instance will have a different value. A field that is created by alternating currents. A sine wave is an example of a time-varying energy source used to energize the electromagnetic field. The workpiece, conductive material can be both ferrous and non-ferrous metals. Some non-metals can also be heated with induction. Some examples include graphite, carbon composites, and conductive ceramics. There's two forms of heating that make up the phenomena of induction heating. One is hysteresis heating. It's friction caused by molecules in a ferromagnetic material switching poles at the induced frequency. Think of a bunch of small magnets flipping from north to south very rapidly. This only occurs in magnetic materials, so above the Curie point hysteresis disappears. The primary form of induction heating is Joule heating, I²R heating. Interactions between the flowing currents and the workpiece giving up some of their kinetic energy when the flowing current collides with the material atomic ions. The increase in kinetic energy develops into heat, thus energy is shifted from electrical power supply to the workpiece. The contribution of hysteresis is small, that for all practical purposes, the I²R losses is the only mode that electrical energy is transferred into the heat for induction heating. There are numerous factors involved that influence induction heating of a workpiece. We'll continue reviewing workpiece material and how the material properties affect fundamental physics of induction heating. This is commonly referred to as skin effect. And Maxwell's equation predicts where alternating currents flow, the current density tends to be higher at the surface of a conductor than at the center. Properties of a conductor that affect skin effect are the conductor diameter, the electrical properties, resistivity, and the magnetic properties, permeability. Furthermore, with alternating current, the current density tends to be higher at the surface of a conductor than at the center. Therefore, the higher the frequency of the AC, the more intense the skin effect. With a higher frequency, the current tends to crowd more towards the surface of a conductor, or in the same sense, to not penetrate as deeply. So this is commonly referred to as reference depth, and reference depth is an unavoidable consequence of skin effect. The reference depth is the wall thickness of a theoretical current, which we commonly call that a sleeve, in which an equivalent power to a solid cylinder is developed. With driving coil current, outside diameter of the workpiece, material properties being equal. So the equation would be D equals 3160 over the square root of rho, which is the resistivity in ohm inches. Stand by. Kelly, we seem to switch to your email.
Sorry about that. Let me, little technical issues here. All right. Let's see, we were on 13.
The broadcast is now starting. All attendees are in listen-only mode.
Okay, so the equation is D equals 3160 over the square root of rho, which is the resistivity in ohm inches, over mu, which is the magnetic permeability, times the frequency, and that's in hertz. Skin effect and reference depth, though related, vary inversely with one another. The greater the skin effect, the shallower or lesser the reference depth. The lesser the skin effect, the deeper or greater the reference depth. So now we're going to talk about the induction heating system components. So the workpiece is the part to be heated. The work coil, this is what conforms to the workpiece areas and transfers electrical energy to the workpiece. Interconnecting conductors, those transfer electrical energy and consist of either buswork or water-cooled leads. A heat station, which is also called a matching station, contains reactive electrical components that build up the electromagnetic energy that drives the work coil. Power supply, this is what converts the utility power to single phase high frequency power to the heat station. Cooling system, water cooling is needed to cool the power supply, heat station, buswork, and coil. Types of cooling systems that are typically used are chillers for low power operations, closed loop recirculating water systems for power supply cooling, evaporation cooling systems typically used in higher, larger installations. Here's how the components are typically situated. So the power supply converts the three-phase AC to DC, then produces a single-phase AC through inverter, IGBTs, SCRs, MOSFETs, etc. A load matching station is an impedance matching circuit to the work coil and the load. So you have your three-phase AC coming in that converts it in the power supply to a single-phase high-frequency output. The load matching circuit of the heat station then transfers that energy to the work coil, and the work coil transfers that to the load. Applications. So induction's used in a lot of different areas, industries. Pretty much every industry can utilize induction heating, but some of the general core competencies of induction heating is heat treating, for heat treating drive shaft components, pins, fasteners, fittings, gears, anything that needs to be hardened, tempered, annealed. Brazing and soldering, example would be valves, electrical components. If you need to braze a contact onto another component using dissimilar metals, you can see a lot of examples there where it's copper and brass, or copper and a silver contact. Hot forming applications, so that would be heating up the part and then forming it into a die. Examples for that would be compressor, rods, cable, bars, structural components. Melting, so anytime you need to make molten metal to form into, example would be electrical connection, engine components. Casting. Bonding or heat staking. Examples, so if we need to, heat staking would be if we heat a metal or a conductive component and then press fit it or form it into a plastic component. That would be a good example of heat staking. Then it fuses the plastic around the conductive component. So lights, shafts, medical instruments, fuses are some examples. And then process heating. You know, if you need to preheat or something like that prior to another application afterwards, or post or pre. Examples would be wire processing, lighting, tubing, switching. Some people would utilize it to burn the insulator off of a wire in a reclaiming process. So they just want the copper wire. They don't need the insulation, so they physically burn off the insulation using induction. So there's various amounts of applications that we always deal with on a daily basis. And I think at this point, Garish is going to talk about some of the applications that they've done over the years, and we have done some as well over the years. So at this point, I'm going to hand it over to Garish.
Thank you, Ryan, for that informative session. I would also like to thank IHEA for allowing me the opportunity and my company the opportunity to present to all of you. I'm looking to basically talk more about the applications that induction is used for. We all heard how induction works in the previous presentation from Ryan. And we would now like to basically spend some time figuring out how and where induction is used in the industry. So there are a lot of induction applications. You know, any application where you need to heat metal repeatably and reliably requires the use or could use induction. So in a manufacturing process, typically, you know, if you had to make 20 parts, you can basically set up the process to basically rig a system to run parts. But when you need to run 1,000 parts a day, 10,000 parts a day, high volume type production, you want repeatability and reliability in the manufacturing process. This repeatability and reliability comes standard from induction heating. Pictures on your screen show some common examples of a brake rotor on the left, shaft type materials in the center. You know, these things are made in high volume. They are made in high production rates. So they require consistency, repeatability, and reliability. So these kinds of applications, therefore, can use or are good fits for induction. I'm trying to forward the slide, and there we go. So why do we use induction? So we just talked about repeatability, reliability. Induction is also used if you need precision in terms of the delivery of the heat. Obviously, if a process that can deliver precision can also deliver generalized heat. But if you wanted to heat just a section of the part, if you just wanted to heat a small portion of the part, induction is a good candidate for that kind of heating. Induction is also extremely fast. 1,000 degrees C or type temperature rises can be expected in a matter of seconds if needed. It is also extremely energy efficient because we saw that the heat is produced directly into the metal. It does not have to rely on media to transfer the heat. That's why induction is energy efficient. Compared to an oven or a gas or a flame type process, induction would be much more efficient given the situation. Induction is also clean. There is no residue that comes off the heating device. Only thing that might come off the process is whatever might be on the part that you're interested in heating. We did talk about repeatability, so I won't beat around that anymore. But when you look at the entire process, in a lot of processes, induction proves to be more economical than any other heating method that might be available. So that is why induction is preferred as a heating source in a lot of manufacturing applications. I'm trying to move to the next slide again. There. So we have a lot of applications that induction is used in. There are numerous. My toughest job being in an applications laboratory is when I have to say no to a process. Everybody would love to hear yes. My sales guys would love to hear yes. Customers would love to hear yes. So there are a lot of applications that are good candidates for induction. There are equally good amount of applications that may not be very good candidates for induction. This is where the expertise lies, and this is what an induction heating supplier can offer when we can evaluate your process. Okay, so if you consider any of the parts, look at anything, any moving part, planes, trains, automobiles, ships, airplanes, the basic building block for all these things is metal. Metal is used to form the skin. Metal is used to form the basic wheels. Metal is used to form the shafts. Everything that's in there is basic metal. And how does metal get produced? Well, believe it or not, induction is used to manufacture metal as well. So this process is called as smelting, to form the basic raw metal from the ore that is dug out from the ground. This kind of process occurs with high volume components, where a lot of mass of material is melted at one time. Because it's a huge amount of metal, a large power supply is needed, because you need to deliver a large quantity of power to be able to deliver that kind of energy. Once you have this molten metal, it is a basic molten metal that's in the form of billets and beams. But if you think of the car, train, automobile, different metal surfaces or different metal parts require different characteristics. The surface of a ship might require a different type of metal than the shaft that is driving the motor. So what happens with this melting process is the metal is taken and then re-melted in the next process, which is basically making alloys from this first melt. Seem to have some problem just forwarding the slide, so I'm going to ask for next slide. So the metal is again remelted and made into an special performance ingot. It's the ingots could be used for shafts, for gears, for cylinders, and depending on what application requirements they have, They are alloyed with different manganese, carbon, sometimes lead, different metals, so that it can perform the function that is needed. Once this melting process is done, you get this special alloy. And now the next process is the forging process, where the same metal is taken and then formed into crankshafts, drive shafts. And again, for some reason, my mouse doesn't say, so I'm going to say next slide. The bolts, they're all made with induction because you can make them repeatably, you can make them economically, you can make them in high volumes. Next slide, please. So induction processes can also be set up as modular type setups. So in modular type setups, you can have a very high volume production without sacrificing the time to heat a particular part or without sacrificing the product quality. Next slide, please. Induction is also used for heat treating. Heat treating processes are numerous and they're used every day to make millions of parts in the automotive industry, in the aerospace industry, in the railroad industry. So all these parts have to be treated specifically to perform a specific function. In the heat treating application, parts are heated to 1600 degrees Fahrenheit and above, and then quenched with a liquid quench to typically get the required hardness and the ductility from the parts. A crankshaft, for example, needs to be very strong on the surface, but very ductile in the center. A gear, on the other hand, needs to be only very wear resistant on the gear teeth. So different processes require different recipes from the same induction heating power source. Next slide, please. There are some new applications for induction. You know, once we have made the bolts, the brake rotors and everything, the industry then requires these things to be painted. For the picture on the bottom left shows fasteners that are painted or patched with nylon patches, that when these fasteners are then installed in automotive or any moving device, they don't vibrate themselves off. With induction, you can use temperature measurement. As you can see on the top right picture, you can get a good idea of what the heat pattern looks on the part. And this can be all integrated in the manufacturing process. So you can get temperature feedback on the fly on the process as you're running it. Induction, next slide, please. Induction is also used to join metals together. Joining similar or dissimilar metals, as the case might be. When you have to join metals, typically a filler metal is used to join these metals together. Depending on the use of these parts, the temperature required in the actual working of these parts, as well as the performance characteristics that are required, the process can be brazing, or as the next slide will show, the process can be soldering. Brazing and soldering are similar processes, but they occur at different temperatures. Soldering is a much lower temperature process, similar to soldering of your in-house plumbing copper tubes. It uses typically a lead or a tin mixture, or in the newer cases with which are moving away from lead, just a tin and a silver type mixture to join different metals together. Next slide, please. Another very common application for induction is called as shrink fitting, where a piece of metal is heated to expand it. Once the expansion on the part happens, it is then basically slipped over another metal piece. And when the part cools down, it basically shrinks and basically anchors itself to the part that it was slipped on. This type of process, as you can see, the parts that are being heated are getting smaller and smaller. So the power that is required to heat these parts also becomes smaller and smaller. So as we are progressing from the initial metal melting to basically refined processes, you can see that the power that is required is getting reduced. But if you notice, the frequency of performance is slowly creeping up. Frequency typically allows you to focus heat better and to basically heat parts in narrower, shallower depths, as Ryan was mentioning with his skin depth equation. Next slide, please. Induction is also used in a lot in the food industry. Juice boxes, toothpaste tubes, Pringles chips packs, any creams, beer bottle caps, they all utilize induction as the type of heating source in their manufacturing process. Now, next time you walk through a grocery aisle, just look at different packaging that is available. And packaging that involves aluminum foils, packaging that involves metal lids is typically all induction application. So there are so many different applications that it will surprise you that you'd not have thought about as being induction applications. And we are finding new ones every day. People will typically approach us and say, we've been doing this for 20 years. Would this be a good candidate for induction, and would it be worthwhile to transfer to induction? Now, this is the result of all the different applications that our company has run over the number of years. Let's go to the next slide. This talks about turbine blade heating. You know, turbines are used in power generation, in land-based turbines. Turbines are used in all aircraft to generate the power. Turbines are also used to transfer liquids and fluids in the oil and gas industry. All turbines have very high stress parts. All the parts that are inside the turbine are either moving at a very fast speed or they're subject to very high stresses. Given that, you want to make these turbine parts from high, expensive, and high-end materials. So when you make these parts from high-end materials, it is customary for customers to reuse the parts by refurbishing them from time to time, because making a new part would be very expensive. So the industry relies on fixing, refurbishing, and reworking these parts to get the most life out of them. So turbine blade heating is a very common application for induction. Next slide. In semiconductor type applications, induction is used to heat graphite substrates, which then in turn heat silicon chips before they are cast or cut into IC chips that go into your cell phones, into your computers, into almost all electronics that we see nowadays. Next slide, please. Induction is also used for odd shaped heating. We do not always have to have rigid copper coils that provide the heating. Induction can be used with flexible induction coils that can be wrapped around parts, that can be basically made in custom shapes. And depending on the part that has to be heated today, they can be then formed to fit the part. Next slide. There is a lot of applications where induction is used to heat metal parts, but the metal parts are then inserted into plastic assemblies. Ryan talked about metal brushes. Car door handles are very common examples of this type of parts. Almost all car door handles are plastics. And the plastic is great because it's very lightweight, but it's very difficult to anchor to plastic parts. That's why a metal insert is heated with induction and then pushed into the plastic assembly. The assembly on the top left has more than 8 different size inserts. The assembly on the bottom right only has 1 insert per part. So the applications are varied, the applications are numerous for this kind of application. The part here is pretty small, so obviously the energy that's required is small. So the power supply that you require to heat some such smaller parts is much, much small. But the frequency that is required to heat the smaller parts is quite high. Next slide, please. Induction is also used in some atypical applications. Manufacturing of cartridges for ammunitions is a typical application that requires the use of induction for any high volume production. When bullets are made, they're typically made 1 per second or faster. At that kind of speed, you need a heating method that can keep up. The heating method not only has to heat the part, but it only is required to heat a portion of the part as well. So again, going back to the basics of induction, induction is able to heat just a section of these parts as well. Next slide, please. Induction is used in some atypical applications like hardening or heat treating of chains. Chains are commonly used in heavy metal pulling, heavy part pulling, and they have to be extremely strong because you must have heard that chain is only as strong as its weakest link. Well, we want to make sure every link is equally strong in a chain so that it can perform to its rated capability. Next slide, please. Induction is used in the manufacturing of chocolates. Again, if you think back, anywhere where you need to deliver heat in a repeated, concise, and a very, very accurate manner, induction is a good candidate. So in the chocolate manufacturing, the cookie that's inside the chocolate is basically made with induction. Next slide, please. Induction is used to burn off enamel of copper wires so that electrical connections can be made to these copper wires. All electric cars, all of the new motors, all of the rotating devices have copper stators and copper rotors, which is basically a bunch of wires that are wound together in a certain format to get the electrical energy transferred to rotational energy. So all of these applications at some point or the other see the use of induction. Next slide, please. Induction is used to make engine blocks for automotive cars. Engine blocks are typically aluminum, but the cylinders are typically steel. Where the piston rides inside an engine block, it rides inside a steel sleeve because steel is inherently harder and stronger than aluminum. So as you can see, the shape and sizes of induction coils can be quite unique when it comes to this type of heating. You have a V6 type heating coil on the bottom right. The coils on the left are showing just heating 4 cylinders for a typical V4 type assembly. So next slide. So we've talked about a bunch of different applications. I want to give a brief recap of what induction is so that you can think about heating, or whenever you think about heating, you think of induction as a possible candidate. Can't promise that it would be a good candidate, but it deserves attention because of the numerous advantages it has. Induction system can also control the temperature of the part that you're heating. So on this slide, going from right to left, the picture on the right showed two pieces in blue. That's the feedback control system that basically shows that you can measure the temperature of the part and then control the induction heating power supply to deliver the energy at a regulated pace. Next slide, please. And this is my favorite slide. We talked about the skin effect and the skin heating. Induction heats from the surface, but it also heats into the surface. And every time I present this slide, I remind my viewers that, come Thanksgiving, you cannot actually put your oven to a higher temperature and hope to get the turkey cooked faster. Because in an oven, all the energy comes from the outside surface and goes into the meat of the turkey. But with induction, you not only heat the outside surface of the part, you also put energy into the thickness of the metal. So this is a key distinguishing feature between induction and oven heating or any kind of radiant heat or hot air heat that might be heating the part. Next slide, please. The frequency of operation can be used to our advantage. For example, you see in this video that the picture on the right shows a large metal part being heated to a bright white temperature. But in that same time, the part on the left, which is a small metal rod, shows no heat. It's cool enough to touch. So the frequency of operation of the generator can be used to our advantage to use different metals inside of the induction heating coils to perform different functions. Next slide, please. There are also software packages that are available today that allow us to basically model the induction heating process before any testing or any heating is attempted. This allows us to get a gauge of the direction in which we need to follow. It tells you the temperature on the outside skin of the part and in the core of the part, and it's able to do it with much less time and cost. Because we don't have to build anything, a person can basically simulate and model these things on a computer and then make iterative changes to optimize the design even before any physical work is done. Next slide. All the data from the induction heating process can be viewed and captured in a computer to be able to analyze at the time of the heating or at a later time to make sure that the entire production run was running through the SPC controls that were set up for that process. Next slide. This software is available. It's basically allows one to put alarm limits. It allows everyone to basically download the data into Excel type formats. So somebody can go back and look at a whole day's run, a week's production run, or even a month's production run to check if the process is working favorably as designed. That is all I have for today. Thank you very much.
Okay, this is Mike again. Thank you, Ryan and Girish, for that very informative seminar. Lots of great information there. Kelly, do we want to do questions now or get through the next couple of slides first, or what?
Michael, you can go ahead and finish up the slides for us. I don't see that we have any additional questions at the moment.
Okay. Yeah, could you advance the slide, please? Yep. Thank you. Again, want to thank our sponsors, Advanced Energy, Heat Treat Today, and Taylor Winfield Technologies. Next slide, please. And one thing we would like to let everybody know about, we are planning to have an induction seminar, a half-day seminar, a little more in-depth than the webinar today. That's in Greenville, South Carolina, September the 19th, which is a Tuesday, 1 to 4:30 p.m. in the afternoon. We're going to talk about arc flash safety, which induction is very electrically powered, and arc flash and the safety of the power supplies is always an issue. Also, we're going to talk about harmonics and some of the potential power quality issues associated with induction. And again, we'll talk about some basics and applications. And you can register for this at IHEA.org website. Registration is open, and we would love for you to attend. Thank you again for everyone that attended. If there's any questions, please type those in or feel free to contact any of the presenters or myself. Do we have any questions?
I don't see that we have any questions, but I would like to thank everyone for attending and just let everyone know that we will have a recording available of this webinar. I do understand there were some technical issues, and I apologize for that, but we will send the recording to all of the attendees as soon as it's available. Have a good day.
Also, one other quick thing. We do have a survey that you're welcome to fill out about the webinar. Thank you very much. Have a good day.